Kruskal's algorithm helps us to find the minimum spanning tree in a connected, weighted, and undirected graph. But what is a minimum spanning tree? It's a tree that contains all the vertices of a graph and minimum possible total edge weight. Kruskal's algorithm is an excellent example of a greedy algorithm. At each step, we choose the smallest edge available, kind of like always picking the cheapest item first. This way, we are aiming to get the best possible total result. We'll be using two data structures for the Kruskal's algorithm. One is a heap and the other one is a set. Here in this figure, you see a weighted and undirected graph on the left side. On the right side, all of the edges have already been inserted in a min heap according to their weights. Here we are using a min heap, but you can also use a sorted list. Purpose of both is the same, to remove the next minimum edge. At the bottom, you see 8 disjoint sets. Initially, each set just contains a single vertex of the graph. As we progress, we'll be combining these sets together to create bigger sets. The idea is to keep getting the edges from the min heap while making sure that we don't accidentally create a cycle. So let's begin. The min heap gives us the edge 80. We remove it from the heap and select it as an edge of the minimum spanning tree. Now here comes an extremely crucial point. Do you see the disjoint sets at the bottom? As soon as we remove an edge from the min heap, we take note of its incident vertices. In this case, the edge AD has incident vertices A and D. A and D are two disjoint sets right now. We take union of these two sets to create a bigger set that contains both A and D. Here we show the union as a curve connecting the nodes. If you can go from one vertex to another vertex following a curve, then they lie in the same set. Let's remove the next edge. It's EH. So we mark EH as a part of the minimum spanning tree. We also note its incident vertices, E and H. Since E and H are in separate disjoint sets, we combine them together using a curved line to make one set. Now removing the next edge, which is FG, it will result in a new set containing vertices F and G. Please verify yourself that so far we've got 5 disjoint sets remaining. We have color coded the vertices. Same color vertices belong to the same set. Next we remove the edge AB from the heap. Now note that A belongs to the yellow set while B belongs to the red set, which is a different set. If that's the case, and if the vertices of an edge belong to two different disjoint sets, we simply combine the sets together to form a bigger set. Here we merge the red set into the yellow set to get a bigger yellow set. Next edge is BD. Both vertices B and D belong to the same set, in this case the yellow set. So we'll discard BD and we won't add this to the minimum spanning tree. Then we have the edge GE. G and E both belong to the different sets. G belong to the green set and E belong to the blue set. So we'll merge both the green set and the blue set to get a bigger green set. Next we discard the edge GE because both the vertices E and G are in the same set. Then we have the edge EC. The vertices C and E belong to different sets, so we'll merge these sets to form a bigger one. Please verify at this point that we have only 2 disjoint sets left. The yellow set contains vertices A, B and D. The green set contains vertices C, E, F, G and H. After that we simply discard edges CH, EF and FC because both vertices of each of these edges belong to the same set. We only merge the sets if both the vertices of an edge belong to different sets. Then we have the edge DE. Now vertices D and E belong to 2 different sets. So we combine the two sets together to get a single bigger yellow set. At this point, all of the vertices are in the same set, so we can stop right here. But just to verify, we can discard the remaining edges BC, CD, AF and DF because both vertices of each edge are already in the same set. We have got our final minimum spanning tree. In the next video, we'll discuss a fundamentally different approach to finding the minimum spanning tree. That's called the Prim's algorithm.